Okay, let's get started. Hello everyone, welcome to the third session of the Probabilistic Machine Learning Reading Group. Today's session will be about Markov chain Monte Carlo, and it will be given by Miguel Santos. Miguel Santos is a PhD student from the Institute of Mathematical Sciences here in Madrid. And with that, the floor is yours, Miguel.
Okay, thank you very much for the presentations. Well, I am going to be presenting the third session, which is Markov chain Monte Carlo, and it's exactly the 12th chapter of the book. To begin with the presentation, I'm going to explain a little bit what is going to be the structure so it is easier to follow. First of all, I'm going to start with an introduction, which I'm going to relate with what Pablo presented in the previous session. And once this is clear, I'm going to go through the basic explanation of Markov chain Monte Carlo. Once this is clear, I'm going to go explain the most famous MCMC algorithms. I'm going to spend more time in the first one, which is Metropolis Hastings, because once you understand this, I think it's the most clear algorithm to understand this idea of MCMC. And lastly, I'm going to also spend more time on Hamiltonian Monte Carlo because it's like the algorithm that make the introduction for the cutting edge algorithm of nowadays. And lastly, when these algorithms are clear, I'm going to explain some concepts about convergence. And if we have time in the end, I'm going to explain some more extensions of these MCMC algorithms, but I don't know if this will be possible. When this is clear, let's start with the presentation. Introduction. What's the problem that we have? Well, I've changed a little bit the notation, but the idea is what Pablo have already explained, which is we have a model built with some latent variables, and we want to train it with some data. So we want to get to this joint distribution, which is the formula you see on the screen. We are going to base the idea on Bayes' theorem. So the idea is to train the model to get the parameters X based on the data, and we apply the Bayes' theorem. This is widely used in regression, in clustering, and even in more complex models such as neural networks. As Pablo explained, to get this exact distribution is really complicated because the evidence is rarely tractable, and also because to get the analytical solution for this problem is almost impossible. So we use some approximation methods. In the previous chapter, we saw variational inference, which the idea was mainly to build a tractable distribution, a function that we can evaluate on based on an optimization problem. This is, we select a function within a family of functions that is the most similar to that posterior distribution that we aim to find. However, MCMC uses another approach, and the differences are the following. First of all, variational inference, as I said, it's an approximation based. We get a function that we can evaluate, but it's only an approximation. In the other hand, MCMC, what it does, instead of getting this function that we can evaluate, we are going to get a sample from that posterior distribution that we aim to find. Another difference is the accuracy, because in variational inference, the accuracy depends on the family that we are working with, while MCMC is asymptotically exact. This is, the more samples we get, the better is our prediction. Also, variational inference is faster and it scales better, and MCMC is slower for high dimensions. It's more difficult to scale, but it's not impossible because the most modern algorithms aim to solve this issue. And when this is clear, we can now start with the basis of Markov chain Monte Carlo. Markov chain Monte Carlo is based on two concepts. First of all, Monte Carlo. Most of you probably are already familiar with this topic, and the idea is that we are going to do random sampling in order to get a sample of the objective distribution, And to compute different quantities, we are going to use these samples. The most common example of this Monte Carlo approach is of estimating pi, which what we do is we sample uniformly in a square, and by counting the points that are within the circle and outside this circle, we can estimate pi. And this is the first concept of MCMC. The second one is Markov chains. What is a Markov chain? Well, it's a sequence of random variables, one after the other one, with the characteristic that the probability of what is going to happen at time t plus 1 only depends on what happens in the immediate random variable that goes before. It's the formula that you see on the screen. Another key concept of Markov chains is the idea of stationary distribution. The formula is not necessary to understand. I want you to understand especially the definition, the intuition, which is a distribution that doesn't change over time. Why is this going to be helpful? Well, if we put both concepts together, the objective, as I have said, is to get a random sample of an objective distribution, P of X. This P of X, as I've said in the problem, it's usually a posterior distribution based on some data, but to make it simpler, we are going to name it only as P of X. That's our objective distribution. And the idea is to random sampling sequentially to get samples one after the other one in this Markov chain scheme. And the idea is to build a Markov chain whose stationary distribution is the objective distribution. Why do we do this? Well, the idea is that the time that we are going to spend in each state is going to be proportional to the density evaluated in this state. So the more time we spend in this state, the more samples we are going to get in this state. And in the final sample, the proportion of this state is going to be proportional to this density. So in the end, it's going to well represent our objective. And once this is clear, I have here some images that more or less explain what we want to do. It's by random sampling. We can see that we're sampling one after the other one. This is the idea of Markov chains. We get then to the objective density distribution, which in this case is a two-dimensional Gaussian distribution. And once we get there, we start sampling, and the samples are proportional. We get more samples where the density is higher, and the opposite. And this is the basic idea. Once we have understood this, we can go to some of the algorithms. The first one is Metropolis Hastings. This is going to be really useful to finally understand what MCMC is. The first idea is that we need a proposal distribution in order to build these Markov chains. We need a distribution to be able to sample one point after the other one. The most basic example is the one you see on the screen, which is called random walk. Why? Because the next sample, we get it by to the previous sample, adding some noise, which is this random step. It follows a normal distribution, center in 0, and with a deviation that we will see what happens with this. And the final distribution is a Gaussian normal center in the previous point. So in this way, we now have this idea that we generate one point after the other. But what happens if we just randomly sample points one after the other one? The points that we are going to sample are not going to be representative of the P of X distribution that we aim to find. And this is where the acceptance probability comes in. Well, we first of all have a minimum between 1 and a quantity. This is because we want the probability to be within certain limits between 0 and 1, and this quantity. The first element of the product is the target density ratio. This measures how much likely is the new point against the previous point. So this helps the function to give more probability to the points that are more likely to be in the sample. And the last term is the proposal correction. This is a correction that it is done to verify how likely is to change from the point that we are in to the next point. Usually, this proposal correction is symmetrical. This is, for example, the Gaussian, this normal Gaussian centered in x sub n is symmetric. So this is usually going to be equal to 1. So if you pay attention, the probability is going to be only how much likely is the new point against how likely was the previous one. And in this way, we enable to resemble this objective distribution. In the book, you can see a theorem that explains why this algorithm work. However, I'm not going to spend time on that. I'm going to show you better a GIF, which is to show what this algorithm does. Here, you can see that this is the random walk on a two-dimensional space in a 2D Gaussian. And you can see at the beginning how it starts from a point, taking random steps. And in the end, when we get to the high density region, we start sampling and we get the final sample from this density. However, this is only an example of one possible target distribution. There are a lot of them, and here we see some examples. The first one is the one I have already explained, which is the random walk proposal, and nothing to say. The second one is the independent proposals, which is the new point doesn't depend on the previous point. This is exactly the idea of importance sampling, which is a way of sampling, which not included in MCMC. And the mixture proposal. The mixture proposal is exactly a weighted sums of different proposals. Also, we have the data-driven proposal, which is that we include when we want to sample from a posterior, we include the data in this kernel, in this transition distribution. And another good idea is to use adaptive MCMC, which the idea is to make this kernel depend on time. Here's an example, which is the same random walk proposal, taking random steps, but this variance depends on time. This is because at the beginning, if we are really far from the region of interest, we can take bigger steps in order to get there. And once we are there, we can start taking smaller steps to move within that region. Not every possible proposal distribution is possible because it has to, first of all, the support of the objective density has to be included in the support of the proposal distribution. This is because if we want to sample points from a distribution, we need to be able to go to those points. If we can get them, they are not going to appear in our sample. And another important thing to have in mind with this proposal is to satisfy some robust behavior. This is because if we give really big steps, for example, if we think in the random walk example, if we give really, really big steps, we are never going to stay within the interest region. And the opposite, if we get really small steps, we are only going to move within a region and we are not going to sample efficiently. And this is what I'm going to show you in the next piece of code, which is I've done the Metropolis hasting for a Gaussian normal distribution with different step size. The step size is measured by the variance of the Gaussian distribution, and here we have 3 examples. The one in the middle would be the right one. As we can see, we have a variance of 0.5 and the results are fine. However, if the variance is too small, the steps that we take are really small and we are not able to get to the other part of the Gaussian. So in the end, we don't get a good result. And the opposite happens if we select a really big variance, because most of the steps are going to be really far from the objective region. So in the end, little samples are going to be accepted and the results are not going to be good. Another thing to take into account, if you remember here the GIF, the starting point is quite important, because if we start really far away, the first samples are not going to be insightful on the result that we want to get. And this is called burning. What is it? Is at the beginning, because we sample randomly the initial a few samples that in the end we are going to erase, we are not going to take into account in our final result to make these first steps. Another thing to take into account is to be really cautious not to start in modes because for gradient-based methods, if we compute the gradient, this is going to be 0 and we are not going to move. And another thing that one can think of doing is to run different chains, different Markov chains algorithm with different starting points. And taking all of this into account, we can compare them and see where to start counting the samples. And these are some things to take into account. Well, before starting to the new algorithm, I don't know if there is any question regarding MCMC, because I want to be clear from this point what these algorithms are. Okay, I'll continue. The next, I don't know if there's a question. Pablo?
No, sorry, I don't know what I
Yeah.
did.
I have a question, Miguel.
Yeah.
Yeah, in the examples, in the three examples, depending on the step,
Yep.
that one. I think on the left one, it's also a matter that you didn't run it long enough. I mean, if you let it run long enough, I would, I mean, you would get a nicer coverage, I would say.
Yeah, that's true. Probably if you're running a lot of time, you end up moving to the other part. That's
Yeah.
true. However, this is for the end of the talk. If you look at the convergence of the algorithm, you might end up seeing that the correlation between sample might be too much, and this means that the exploration haven't been really successful. You might get some good results, but the convergence might not be satisfactory. So you have to look for these convergence results in the end to test whether it has worked well or not.
Can I make a question, Miguel?
Yeah, of course.
Yes, when this support containment, does it really have to be in only one step that you have that the support of P is contained in that support, so that that means that you can get in just one step from any point X to any point in the support of P, no? But maybe if you had like I don't know, truncated Gaussians,
yeah,
I have the feeling that it would work also, no? Like if you can get in a finite number of steps to the support of P, that would be fine, no?
I mean, if there's a point where the support of P is included in some step, you will be able to get there. But the idea is in general, if your support is never included, you are never going to be able to get there.
Okay, thanks.
No problem. Well, if there's no more question, I'm going to continue with another algorithm, which is Gibbs sampling. The idea of Gibbs sampling is to apply MCMC to multivariate distributions. The idea is to update one coordinate at a time. This is the formulas for a 3D distribution. Very simple. You first sample the first one, condition on the other ones, and so on. The second one condition on the first and the third, and the third one condition on the first and the second. And you repeat this until you get the number of the desired sample. For a d-dimensional scheme, this would be the formula. To get to still be having that random walk examples in our head, I want to show this image, which shows the difference. In the first one, the Metropolis Hastings, you take a random step in any direction. And in the Gibbs sampling, is almost the same, but you get the steps in each directions. You move like if it were, like the Manhattan distance, you move with square angles, 90 degrees angles. The good thing about this is that for these exact examples where we are sampling from a 2D Gaussian, we already know that the conditional distribution of the marginal distribution of one of the coordinates is also going to be a Gaussian condition on the other variable. So for us, it's really easy to sample from this conditional distribution. However, what happens if we don't know one of these conditional distributions? Well, the good idea is that we can combine this with sampling with Metropolis Hastings we can combine these Gibbs steps with Metropolis Hastings to sample from these conditional distributions. And some more comments about Gibbs samplings are that there are some extensions. One of them is block Gibbs, which the idea is that instead of sampling one by one in every direction, you can group the variables. This is you can first of all sample for the first two, then from the third, the next ones, and so on. This is usually done in some cases. For example, in Gaussian mixed models in clustering, you can sample from the means at the same time and then from the latent variables. In this way, you avoid the correlation between that these conditional distributions can have. And another extension is collapse Gibbs, which is similar to block Gibbs, but it's not to group the variables and sample in groups. Is you integrate some of these variables and you only sample from the ones that you haven't integrated. And once you have the posterior of the non-integrated variables, you can now go with the ones you have left behind. This is also used in Gaussian mixed models. The idea is that, for example, you integrate the mean and you sample only from the latent variables theta 1 to k. And once you have the points, let's say, arranged in different clusters, you now sample the mean of these clusters. Let's go to the next famous MCMC algorithm. This is auxiliary variable MCMC. The idea is that for some distribution, it might be really difficult to get the distribution to sample from P of X. So we introduce an auxiliary variable. Why this? Because later, computing the marginal distribution, this could be a sum or an integral, depends on if we are a continuous or discrete distribution. But the idea is we introduce this auxiliary variable because sampling from the joint distribution or even the conditional distribution in this Gibbs scheme that I have already explained is much easier. And to understand this, we are going to see the most famous example of auxiliary variable MCMC, which is slide sampling. So we introduce this auxiliary variable U, so that the joint distribution is going to be uniform with this constant that is the normalizing constant of the objective distribution, which we don't actually need to know. But the idea is that sampling now from a uniform distribution is much easier than sampling from a P of X that we don't really know about this. Also, it's important to have in mind the region that the uniform distribution is defined. Only on the values that are smaller, well, greater than 0 and smaller of the objective density. And why this works? Well, the idea is that if we compute the marginal distribution of P of X with this formula, we can get by computing the uniform distribution, we can get this marginal distribution. And what is going to be the algorithm? We are going to again to use the Gibbs scheme to sample one depending on the other, and the steps are the following. We have X of t, and we sample the next U auxiliary variable uniformly from the interval 0 to the density distribution evaluated in this point. Once we get this sample, we can now sample the X variable based on uniformly, again, from this region, which are the points whose density is greater than the previous uniform variable. Why this works? Well, to see it, I'm going to show you an example on why this works. First of all, I want you to pay attention to the right graph, which is the objective density function, and then to the one on the middle. Why? Because if you remember, the region that we have defined, the density is exactly the same. Well, it has exactly the same shape of the objective density. This is because in this region that you can see in the heat map, we get this uniform distribution, and by sampling, we sample in a 2D. We get also the samples in the joint distribution, and by marginalizing, we can get the distribution of the 1D distribution. And this is the basic idea. There are more examples of auxiliary variables, and one of them is Hamiltonian Monte Carlo. Hamiltonian Monte Carlo is most known to be as the first gradient-based method, but it is also an auxiliary variable method because we introduce a momentum. Well, HMC, Hamiltonian Monte Carlo, was first born to introduce the gradient in these sampling methods, and it is also designed to cope with one of the problems that MCMC had, which is sampling in high dimensionals, that difficulty to scale. And this is what Hamiltonian Monte Carlo does. It enables us to improve in this context. How do we do it? Well, we introduce the auxiliary momentum, which is sampled from a normal Gaussian distribution with some matrix sigma, which is called the inverse mass matrix. And we are going to base our sampling in the Hamiltonian. The Hamiltonian is the energy of a system, and we have the potential energy and the kinetic energy. The kinetic energy is the moment associated with the momentum, with the velocity, and because we want to sample from P of X, our objective distribution, we are going to define the energy as the minus the negative logarithm of P of X. Why do we do this? Because Hamiltonian dynamics, what it does is that you move around the space trying to minimize the energy. And if we minimize the energy, we are going to maximize the probability. So in this way, we are going to explore more the points whose energy is low, which means that the density is high. This algorithm is based on physics, and exactly it's based on Hamiltonian dynamics. Here you can see the formula of the differential equations. However, in order to solve these equations, we apply some numerical approximation. Here in this image, you can see the idea of Hamiltonian Monte Carlo, which is, again, we have a starting point and we move. In this case, instead of moving within a random step as in Metropolis Hastings, we are going to move based on those formula, those derivatives, following the Hamiltonian dynamics. Again, we want to go to the low density regions, energy regions, which are the high density regions of the objective function. Again, we can't solve the numerical. We're going to solve the differential equation with a numerical approximation. This numerical approximation is called leapfrog integration, which is the formula that you see on the screen. I'm only going to make a comment, is that this plus 1/2 has been introduced to make this approximation symmetrical. So it's the same to go to one point that to go backwards and make it more stable. Another thing is the hyperparameters. Again, we have the step size, which is the idea is again the same as of the Metropolis Hastings. How much do we move each step? Also the mass matrix, which is the one involving the kinetic energy, and lastly the number of updates. This is the number of mini steps that we are going to get before going to the next possible point, the next sample point. And in the end, we also introduce an accept reject probability, same as in Metropolis Hastings. This Probability is the same definition, however, in terms of the Hamiltonian is the expression you see on the screen. It is very interesting because this probability is not created in order to make the sample distribution, the sample follow the objective distribution, because this is done by the Hamiltonian dynamics following that gradient descent, looking for the minimal energy point. The idea of introducing this accept reject probability is to make the algorithm more stable, because in theory, in Hamiltonian dynamics, the energy should be constant. So this difference, it's expected to be equal to zero. However, as we are using this numerical approximation of the differential equations, this is not going to be zero. So it is introduced to go always to lower energy states, because if the energy of the new state is much higher, we are going to get really far from the density region. So it is more likely to diverge. So in this way, we control the total energy of the system, allowing only for transitions to lower energies, and we control a little bit the convergence to make it again more stable. And I know this slide is not really intuitive, but I wanted to put it because again, Hamiltonian Monte Carlo has these three hyperparameters, which might end up being a problem. And the algorithm is the following. If we want to get n samples, we are going to, for each sample at the beginning, we sample the new momentum, this auxiliary variable. And based on this momentum, we take L steps of the leapfrog update until we get to the last point. And once we have this last point, we decided to accept it or to reject it. Again, we have these hyperparameters, which are actually a problem, as we saw in the metropolis testing, because too big, we are not going to get within the region, and too small is going to take us a lot of steps to converge. And to solve this problem, appear a new section of Hamiltonian Monte Carlo, which is called NUTS, no U-turn sample. The motivation is what I've said, not to manually adjust these hyperparameters. What this algorithm does is that in order to choose L, it runs several chains at the same time, one backwards and one forward. This is because we have the momentum, so we can go with plus the momentum or minus the momentum. And the paths that start behaving weirdly, we can erase them. And also to choose the step size and the mass matrix, the idea is to, during the burning period, compute them and see which of these behave better. And to show you a little bit the importance of these hyperparameters, I have this image prepared, which, well, first of all, the first one is the random walk metropolis Hastings. This is not a 2D Gaussian distribution. I've made this in a 50 dimensional space. I have only projected the first 2 dimensions. First of all, because I wanted to show how good Hamiltonian Monte Carlo is able to scale to higher dimensions. And the problem that we had with more simple MCMC algorithm, which can be seen here in random walk metropolis Hastings, where the sample is clearly far away from the objective distribution. Now here in the middle, we have 2 Hamiltonian Monte Carlo results. The first one is for a rather big step, equal to 7, where we can see that it is close. However, in this part, we lack some results, meaning that we have started over here. And then if we rightly select the step size, we get this nicely distribution. And lastly, we have the nuts, where we didn't choose any hyperparameters, and in the end, it ended up making a good results. And this is why this algorithm was really useful for Hamiltonian Monte Carlo. Another extensions that we have about Hamiltonian Monte Carlo is about the the mass matrix, the one that was included in the kinetic energy. This mass matrix, this extension is called Riemann manifold, and the idea is to adapt the geometry of the system, changing this mass matrix to the local behavior. And two examples is the Hessian and the Fisher information matrix. That this last one, it's really used nowadays. And another extension is stochastic gradient Hamiltonian Monte Carlo. This is born as a result of what has been done in other studies. For example, everything started with Langevin dynamics, which is more or less a special case of Hamiltonian Monte Carlo, which L equal 1. This is we get only one step during the leapfrog update, which the idea is that computing the gradient is really cost. This involves computing the gradient in all the data we have. So instead, we compute the stochastic gradient by separating the data in mini batches and random sampling from this and computing the gradients. This is also used, sorry. This is also used in with some variance reduction techniques, which is to get a reference point and compute the new gradient using the batches, the mini batches, but with that reference point in order to reduce the variance. And having these things into account, we get to a stochastic gradient Hamiltonian Monte Carlo, which what does is compute the gradient with some noisy estimation that we call it G, but this G can have, I don't know, you can include here the mini batch thing. Also, you can include the variance reduction technique. You can also include the Riemann manifold approach, the ones the user want to use. And the new upgrade will be, instead of using the gradient, we use this approximator. And now we've seen this, another important thing that I commented during one of the questions is convergence, because the convergence of the Markov chains depends on how we define it. So usually, instead of previously checking for convergence, the usual thing to do is you run the algorithm, you run the MCMC, and once you get the result, you check whether the convergence is satisfactory or not. And these are the motivations. The first one, I have already talked about it, which is the starting point, because if we start really far from the distribution, we are not going to get anyone. And the solution is only the burning period. However, the second motivation is to check whether the Markov chain has been worked properly, as I said, if it has converged or not. There are different approaches. Usually you combine some of them. The first one is to run multiple chains. And the idea is that if the chains have behaved similarly, the algorithm has converged. However, if not, you will have to look for a solution. Another idea is to look for autocorrelation. This is to compute the correlation between the samples at time t against the sample at time t plus L. The idea is because Markov chains, as we sample one sample after the other one point after the other one, it's impossible to get rid of autocorrelation. It's impossible. However, the lower this is, the better. And another quantities you can compute is the potential scale reduction factor, the R hat, which compares, this is if you have run multiple chains, that compares the variance within that chain, again, the variance, taking into account all chains. So the idea is that this should be similar because they represent the same distribution. This value is recommended to be next to, it's always greater than 1, and the closest to 1, the better. And another thing to have in mind is the effective sample size. Yeah. Here we, using the autocorrelations, we compute this value, which is summing of all the correlations. And then we compute we divide the chain length divided by this value. Why do we do this? Because if the Markov chains was ideal, which is impossible, these autocorrelations will all be 0. So in the end, this value is going to be 1, and the effective sample size is going to be exactly the chain length. However, this is never possible. So the bigger the effective sample size, the better. And here I'm going to show you again, I have used the same Metropolis Hastings algorithm with the 4 variants. You can see here again the setup to get the different behaviors. Here in the first one, as one of the questions said, if we run the algorithm more times, we will be able to get to all places. However, you can see that clearly the chains behave really similar one against the other one. They go everyone to one point. The one in the middle, which is the one that behaves correctly, you can see that we are not able to defer one chain against the other one. And lastly, the last algorithm, the steps are really big. So in the end, we have this, let's say, weird behavior that is not good to have. And lastly, we can look at the autocorrelation plots. In the x-axis, we have the lag, the L of the autocorrelations. We see that for a well-behaved MCMC, we get that they decrease at the beginning in a nice rate. Again, I say that it's impossible to have zero correlation, and then they start oscillating a little bit. However, both of the other ones have this autocorrelation functions, which tell us that we should look at our algorithm to check for it. We can also look at the statistics that I said, the R hat, that the one in the middle is the one that behaves better, that is closest to one, and the other ones tend to be higher. And lastly, it's really important to look at the effective sample size that tell us that the first and the last algorithm, the number of the effective sample size is really, really small compared to the one in the middle. So again, this tells us that even if we could have approximated well the distribution, we have to look at our chain to make some changes and improve the results. And this was about convergence. I don't know how much time we have left. Maybe
I think we have plenty enough. I think you can keep going. Whatever you prefer or as you see fit.
Okay, perfectly. Maybe we can, if there's any question, we can answer right now, and if then we have more time, we can go through the extensions and the conclusions.
I have one super quick one regarding the effective sample size.
Yep.
Does it have any meaning? So in the meaning, so in the plots you just showed, yeah, so there you're getting 3,000 samples, but then the effective sample size for the correct one is around 400. So should we do something in regards to that?
Do you mean in this middle example?
Yeah. There the effective size was 400. So should we just, I don't know, sample 400 samples, or like should we do something about it?
The idea is that you are not going to here, as you said, we get 3,000 samples, and the effective sample size is only 400. The idea is it's impossible to get the 300. As I said, there's always be a correlation. The less correlation, the better. Here, it is true that maybe you could get better results because it decreased really good, but then the oscillation might be really high. But another thing you can do is it's a method called thymine, which what it does, it's that from all the samples that we get, we take a sample each 10 steps. For example, 10 steps, you can choose 10, 20, or whatever. And only the other ones, you erase the other ones, and you only maintain the samples. This will reduce a lot the autocorrelation because you are changing the lag, and the sample, you are going to reduce this correlation. However, the statistical information is going to be the same. And yeah, I don't know if that has answered your question.
Yes, thanks. So yeah, I think you can keep going if there are any other questions.
I have one, Miguel. in the plot you just put, there was a table in which there was, yeah, so that there the column for the accuracy rate. What's the intuition? Because for a lower sigma, the accuracy seems to be better, but I don't know if that's
Yeah,
right, or how
sorry.
do you understand that?
Yeah, I forgot to explain it. This is not the accuracy rate, it's the acceptance rate. As we are using this Metropolis Hastings approach, the acceptance rate is related to the probability that the sample we have generated, if we keep it or not. If we see the acceptance rate is always of the last one is really small, this means that the steps that we are taking are really far from the density region. So in the end, we reject a lot of samples. And if the step is really small, the acceptance is really high. This is because we are always going to move within the region, so most samples are going to be selected. It is recommended that this acceptance rate is always between 0.2 and 0.85. This is also one reason that even the middle distribution might look good, better than the other ones. We could improve it, but it's not the accuracy rate, it's the acceptance rate.
Okay, thank you. So the idea is that you want to
Yeah,
not always accept, so that you're exploring a bit farther in the distribution, but
exactly.
but also being able to not always be explore too much and actually estimate correctly the distribution that is your goal. No?
Yeah,
Something.
exactly. You want to be within a reasonable interval to have proper results. For example, if you remember in Hamiltonian Monte Carlo, we also have an acceptance rate. In Metropolis Hastings, the acceptance rates, as I've said, usually you want it to be between 0.2 and 0.85, 0.9. However, in Hamiltonian Monte Carlo, as the acceptance rate was more related with the energy conservation, usually in that algorithm, the acceptance rate, you want it to be higher because it means that you are usually within the energy interval that you have started with. But for Metropolis Hastings, yeah, you want this to be the acceptance rate to be within this interval. Any more questions? Okay, so I have some more time, so I'm going to continue. The first extension, reversible jump MCMC. This algorithm was born in order to keep with MCMC, but when the dimensions of the parameter vector is not fixed. An example to understand this is a Gaussian mixed model where we don't actually know how many clusters, how many means are we going to be using. So the Markov chain state is right now is not only the means. You introduce an integer, in this case k, where you measure in what dimension you are, and theta sub k is going to be it's going to vary. This is if we are in dimension 2, for example, we are going to have two values, but this can be changed. So now the new posterior distribution depends on k and on theta. And the key idea of this algorithm is to make to introduce some function, some transition function, which enable us to change from one dimension to the other one. And this little bit the idea. We have the model in a certain state, the dimension and the parameter value, and we also introduce first a density. This density, which enable us, is to change from one dimension to the other one. Usually, this is for example, in the Gaussian mixed model, this is whether if the probability to upgrade the dimension by one, this is to include another cluster, or to reduce it. And also we need an auxiliary variable, because if we are going to upgrade the number of parameters, we need that if we, for example, go to one more dimension, we need a way to introduce a new value to the new parameter that we have created. And lastly, these auxiliary variables have to include some functions, which one has to be the inverse of the other one, which enable us to move from the parameters from one dimension to the other one. So everything is well defined. That's the key point, to define well the transformations to go to one dimension to the other one. And again, we have the acceptance probability, but the formula now is much more longer. We have the posterior ratio. This is how likely the new point is, that we already have this. And now we have the transition, these two values, let's say, are the how likely the transition was. How likely is to go from one dimension to the other one, compared to the reverse change, against the how likely the new parameter is based on what we previously have. And also we need this term, which is the absolute value of the Jacobian of the transformations, which is used because it has no sense to compare a probability function defined in for example, in one dimension against a probability distribution which is defined in two dimensions, because let's say the magnitudes can't be compared. It's like in physics, if you divide to compute a probability squares meter, meters squared to meters. If you divide, the dimensions are not going to cancel each other, so the results are not going to be good. It has no sense to compare this, and this is why this factor is introduced. And with this, I'm going to show you some results, which is the idea of what happens with this algorithm. I want to pay attention to this middle graph of this MCMC algorithm, that we can see that we have, it's done in a Gaussian mixture model, that we can see how the different k change to the different possible values. We can see that at the beginning we have this burning period, this transition period, where the algorithm kind of tests the different possible k values, and in the end it reaches a point where it finally decides, based on the likelihood, that the right one to be working with is k equal to 3, and in the end the posterior distribution of k it's only be included in this possible k value, and we don't have to previously assign this hyperparameter. The algorithm itself is able to change from one k to the other one. And last extension is simulated annealing, that is to use this MCMC setup instead of sampling from a distribution to find the global optimal of a distribution. To do so, we introduce a T parameter, which in the negative exponential, again, this energy is the same that we have defined for the Hamiltonian Monte Carlo. And the idea is to make T evolve in time, so it starts decreasing, and by doing this, we go to the distribution that we have, to a distribution where the bigger the mode, the bigger the global optimum is, the more steep the function is. Here we have, I took this image from the book itself, and if we have big temperatures, the distribution is rather flat, like all the modes seem the same. However, when we start decreasing the temperature, the bigger nodes start to grow while the other ones start to decrease. And while we get closer to zero, we can see that the global optimum is the objective. And by using MCMC in this setup, at the beginning, we will be able to sample to move to one mode to the other one. But when we start decreasing the temperatures, the algorithm itself is going to tend to converge only to this global optimum. So by mixing the temperature, we are able to explore the whole area, and in the end, getting to the point that we really want to be ending in. And this was everything about MCMC. I hope it has been clear. We have explored, first of all, the key concepts under MCMC, which are Monte Carlo and Markov chains. We have also seen different algorithms, Metropolis Hastings, auxiliary variables, Gibbs, and Hamiltonian Monte Carlo. Lately, we have seen more the cutting-edge gradient-based methods of MCMC, which include that mini batching for Stochastic gradient, also NUTs for avoid hyperparameter tuning. And we also have seen in the end some convergence methods to see whether our Markov chain has well behaved or not. Lastly, if you want to code your own simulations, you want to use Python, NumPyro, PyMC, and Pyro both work pretty good. The simulations I've done it with NumPyro. However, all of them work pretty well. And away from Python, you could use Stan or OpenBags to run your own simulations. And some extra reference. I know I've gone fast through Langevin dynamics because I use it only as an introduction to explain what Stochastic gradient was. Here you can look for it. Also, another extension of Hamiltonian Monte Carlo is by including repulsive force and more things about random jump MCMC, reversible jump MCMC could be found in this paper. And lastly, one question that I've been answered during the presentation is thinning for reducing the autocorrelations. And that was everything. The next session will be on December 17th about chapter 13. This is about sequential Monte Carlo, and Mario Chacon will be giving that session.
Okay, thank you so much, Miguel, for this really interesting and thought-provoking talk. Are there any questions?
I've got one. Well, first of all, Miguel, excellent talk. Very clear even for me that I'm not a mathematician. So excellent job. The question I've got is just simply, how do you apply these methods to machine learning? As far as I know, Pyro is a package for implementing Bayesian neural nets. And there, most of the methods you have mentioned, Metropolis and Gibbs specifically, and Monte Carlo Markov are being used. So what is the applications? And the second question, if you allow me, is what kind of problems we can solve better using these methods than using variational inference?
Okay, the first question relating the software, the applications, you can actually use every model that you can imagine that, for example, neural networks that nowadays are trained using only gradient descent to get in this frequentist approach a point estimator. You can use it in the same way. You define the model the same, and instead of running gradient descent, you get this MCMC approach, and you will end up getting a sample of the parameters of the distribution. And you can the same way compute the predictions, and you in this way, as you are getting a density of a sample of the distribution, you can also get a sample of the prediction as in any other model. You can apply it from a linear regression to a more complex setup. Of course, the more complex, the more time and computation effort you will need.
So you say not only the Bayesian neural nets, but also algorithms like transformers or diffusion models can benefit from these methods?
I'm not related. I mean, I don't know if those methods are used, but if you define the model, I would say, I'm not going to say I'm sure, but I would say that you can train it similarly as if you train a regression model.
Okay.
Can you repeat the second question, please?
The second question is industrial applications. Started with Bayesian neural nets, and finally I didn't trade them in the field of renewable energies. Why? Because they are basically conditioned by the methodology. So in that kind of fields that we have a lot of uncertainties, I think Bayesian methods are very good. Probabilistic machine learning as a whole is good. So how you
As I
work
said,
with
in
particular problems,
in these approaches, in the end, you don't only get a point prediction, you also get a distribution of the possible prediction. But this also
Right.
has this another another key point, that is that if at some point you get some data, you can train the model using MCMC with that data. And if the next day some more data comes in, you can train things, let's say, sequentially. Like the posterior of today is going to be the period of today. And this is another good point of Bayesian computations that you can take advantage from. You don't have to run every day with the whole data that you have been storing.
If I can jump in, regarding the comparison to variational inference, I'd say that it's mostly about scalability and whether you want an exact result, even if it's super costly computationally, and even if that's possible, but then when you go to high dimension, you need to get some approximations because exact results are not even possible once you get to super high dimension, so speaking deep learning kind of thing. And then I'd also want to comment on, like, this is all open for discussion and we can keep on discussing things in the group chat as well. But yeah, I see there's another question by Daniel, and then I'll read the one by Max as well in the group chat. So Daniel, if you can unmute yourself.
Yes, can you hear me correctly?
Yeah.
Oh, fine. So we saw that Metropolis Hastings was good because it was pretty general and could be used in any problem, and that NATS and the HMC in general was good because it was scalable. So I would like to ask, when would you like to use Gibbs?
Okay, Gibbs is more used when you really know the conditional distributions. If you know the conditionals and you have a really fast, let's say, a really fast way to sample from those conditionals, Gibbs is much faster. Because you don't have to use. I said that you can combine Gibbs with Metropolis Hastings or Gibbs with other algorithms to sample from that conditional distributions. However, this is more costly. But if you know the conditional distribution, for example, the sample I gave, if the condition of a Gaussian distribution is also Gaussian, so that is really easy to sample from. In those cases, Gibbs is suggested.
Okay, thank you.
Okay, and I also see there's a question by Max. He says, thanks for leading the reading group, and whether you have any intuition or examples about why we shouldn't start at a mode for gradient-based samplers.
Yeah, the idea is if you exactly start at the mode, the gradient is going to be equal to 0. So you won't move from that point. In the practice the starting point is usually done randomly. So you are theoretically, the probability to start a point in that point, if the distribution is continuous, is 0. But to have in mind, because also in this numerical approach, if the gradient is really small, it's going to be approximated to 0, and you will end up with getting no samples at all. It's only in reality, you won't have that situation, but just in case.
Okay, he thanks you. Are there any other question?
Miguel, I think in the last session, a question came up regarding the usage of both variational inference and MCMC. Maybe we want to reflect on, I don't know if you have an idea of how to use both of them to like leverage the benefits of both simultaneously, or maybe we can reflect on this on the next session of the reading group.
Okay, well, I don't know if Pablo that gave the other lecture has something to say, but for example, I don't know if you remember that I explained during the Gibbs sampler, I explained what was the collapse Gibbs sampler, which what it does, if you have lots of variables, you integrate some of them, and in the end, you only sample, you are only going to get a sample from the ones you haven't integrated. So you could, for example, use Gibbs sampler from this when it's easier, for example, and then the ones that are left, the ones that you have integrated, you could use variational inference to compute those. For example, in a Gaussian mixture model, you could use Gibbs to sample from the latent variables, whether a point belongs to one cluster to the other one. And once you have that information, you can apply that to approximate it from a mixture of Gaussians. That's an example that I come up with, but the moment I don't know if there's some other application going on.
Okay, yeah, thanks. I think we can also discuss it in the next session if we have some time. Perfect.
Okay, perfect.
Okay, so if that's all, I think we can conclude this session, and yeah, we'll hopefully see you in 2 weeks. So thank you all for coming. Bye.
Thanks a lot.